Firstly, regarding project. So the project was released. The TA who's going to be in charge of the project is going to be Jorge. So if you have any questions regarding the coding aspect as, itself, the repository, then he's the person to go to. So his office hours, I believe, are going to be on Wednesday. So I do encourage everyone to just go through and download the repository, download the SAM model, and make sure everything is working, because I think that will take quite a bit of time. If you have not worked with any kind of IDEs, for instance, just getting that to work will be a challenge. So please do that as much as possible within this week. Try to finish that within this week to make sure that everything is set up. Once you have it set up, then you can start looking at the other parts of the project, which is we need to generate the ground truths for all of you. Since there's a lot of people here, I put this in the description sheet. Essentially, there is no ground truth in terms of prompting. The same prompt, you can give and your friend can give. These are different prompts, but you'll get the same segmentation mass at the end of the day. So there's going to be different amount of different kinds of ground truth. And so that part is something that you will generate and then give to your friends. Everybody else within the class will get access to these everybody else prompts, essentially. So you can use that in order to improve your model. Also, the number of data sets, I think there's about 18 or 19 data sets. It has not been optimized across all different data sets. Again, Jorge is a person who is doing this with another grad student, so they have not been able to optimize it across data sets. So sometimes you will notice that some of the images might be out of the frame, essentially, or the points that you are clicking within the prompts themselves may not be recorded correctly. We are in the background trying to make sure that everything is optimized, but if you find something, please let us know. So this is all on GitHub, so it's a public repository that you'll also be able to go through and contribute to the repository. I think one of you already did that, which is, thank you. I think that is very helpful for the project and for everyone else as well. So in summary, make sure that the SAM model itself is working. Try to make sure that that is done within the end of this week. If you have any questions, please come to Jorge. He'll be the one who will be able to help you to make sure that the SAM model is running and all the framework itself about the prompting is running as well. You should also have access, I think in the Google Sheet, you should also have access to the data sets. So there's natural language data, there's natural image data sets, and there's a subsurface image data set, there is a medical data set, and there's also underwater data set. So all these different data sets, some of their, let's say, parameters are going to be different. You will not be able to get like a very high IOU of 0.9 on medical data sets at all. But you should be able to get something like that in natural image data sets, but not in medical or even the subsurface seismic data sets. So if not, you're not getting 0.9, it's perfectly fine. You can go through and do the best possible within 2 tries and then see the IOU that you're going to get within those data sets. Any questions about the project for 8803 and the people from 4803 have signed up for the projects? All right, if not, I believe those are the logistical things. I did have one thing to mention about homework 3. Many of you noticed that in homework 3, I think it was question 3, your MSE was very high. I think it was about 3,000, 3,500 or something like that. And again, the question 3 is a very derived question. You have noticed that we literally took out a feature and then linearly combined a couple of features, put it in. So our goal was to show you the difference between full rank and low rank. But ideally, if you want to have a good MSE and if you want to solve it, you need to normalize your data. If you see your X ranges, I think the maximum of your capital X is like 0.5, while the maximum of your Y is like 350 or 360 or something like that. So that should not be the case, right? So if you really want a good model and if you want to get like low MSE similar to question number 1, you would have to normalize Y to make sure that it's between 0 and 1. And if you do that, you'll notice that your MSE is going to be very less. But I don't think I talked about it before, nor did I answer this on Piazza, because as soon as you normalize your data and put SVD, then it's a different method. It's called PCA, which is Principal Component Analysis. Depending on the way you normalize your data, you'll have different dimensionality reduction techniques. It could be PCA, it could be something like a ZCA, which is Zero Component Analysis, where not only do you normalize, you also decorrelate the data as part of this kind of pre-processing. We'll come to all those things later, but now if you are interested to make sure that you are getting a good model, then you can go back to your codes, and if you normalize the data, you'll get better solutions. But of course, all of you have submitted homework, it's not important at all. This is just as an FYI. If you are ever wondering that, 3,700, if it's a good MSE, it's not a good MSE. Our goal was to, in fact, show you some, in this kind of exacerbated scenario, just to show you what results will look like between full rank and low rank matrices. All right, with that, those are the logistical things I wanted to cover. So with that, let's get back to the lecture. So this is going to be the second lecture on clustering, and hopefully this will be the second to last lecture on clustering as well. From next week onwards, we can move on to neural networks. Wednesday, we'll finish clustering. So what we discussed last time was some basic definitions of clustering, and we put in some constraints for ourselves. We wanted to make sure that every point was within a cluster, the union of all points would form the entire data set, and there was some kind of a proximity or distance measure that we were using. We covered quite a few distance measures in terms of Euclidean distance, Manhattan distance, Minkowski distance. There was one distance that we did not cover, which is Mahalanobis distance. This is probably one of the most important distance measures. In high dimensional spaces, you want to use something like a Mahalanobis distance measure. The reason is that not only does it take the 2 points that you're using in order to calculate the distance, but it also has access, you also have access to this thing called sigma, which is your covariance matrix. So maybe I can show you an image to better motivate what this means. The difference between something like a Euclidean distance and Mahalanobis distance is that in Euclidean distance, given 10,000 data points, when I ask you distance between 2 points, you only need those 2 points in order to make a observation. So in this case, if I ask, if here, I guess there are about 1,000 red points over here, and if I were to ask you what is the distance between x2 and x1, you're going to take whatever this point is, and calculate simple Euclidean distance and tell me, right? So that is a distance from a very simple Euclidean L2 sense. That would be the distance. But the problem in this case is that you're only looking at these 2 points, and you're not taking the other data points into consideration. You still have 1,000 different data points, all of which exist in this space, but you're not using that in order to create distances. Now the question may be, okay, is it really important to use all the other ones? Because when you're looking at distance, inherently we are just looking at 2 options over here, which is that you have 2 data points at different parts of your space, and you can just take a simple measurement between the 2 things. But data generation is very important. So if I have, for instance, this kind of a data generation process, where let me say that everything is like this. This is a good Gaussian data generation process. If I were to ask you what the distance is between this point here and some other point that is over here, let me call this as x1 and this point as x2. The x2 point is not something that we expect from this data distribution, right? It is what we would call an outlier. It's somewhere out of our data distribution process. So the likelihood of x2 existing is very low. That means the distance from x1 should be high in a sense, because it's not about the physical distance about x1 and x2, it's the likelihood of whether this data x2 actually can exist or not. In that sense, x1, x2, some kind of a distance x1 and x2 should be very high, should be very, very, I don't know, I'll put it as 10,000 or something like that. So let me give you another data point here, x3. So this is x3. Now physically, if you look at the distance between x1 and x3, you'll notice that they're much higher. It's a pretty long measurement between x1 and x3, but it's within the same data generation process. It's not very unlikely that x3 will exist and x1 will exist at the same time. So in fact, what I want then is that distance of x1 and x3 must be very less, let's say 1. In our normal Euclidean distance setting, we cannot get these outputs. We cannot get 1 in 10,000 for these things. What we need is an additional factor that we're going to call sigma that is going to help us with understanding what the data generation process is. Given a data generation process with a function sigma, I should be able to now make a decision about d of x1, x3 being a very high number, which in this case can be 10,000, versus x1, x3. I'm sorry, I don't know what I said before. D of x1, x2 needs to be 10,000, and then d of x1, x3 has to be a much lower number, which is 1. And the distance that is going to allow us this is something called Mahalanobis distance. Again, this might not make too much sense in this kind of a 2D setting. Hopefully the motivation is clear from a 2D setting. But if we come to a high dimensional data set where we are dealing with 10,000 different features, it is very essential that we take the data generation process into consideration as well. Because if we only have 2 features and we want to create 2 data points, then Euclidean distance can be a good measurement. But from 2 data points, if we are to calculate distance between 10,000 different features, Euclidean distance may not be a good methodology. In high dimensional representation spaces, Euclidean distance is not good. This is when we have to think of other things. And Mahalanobis distance is a good way of trying to find it. So then the question becomes, okay, what sigma is? And sigma is basically your covariance matrix. When it's an identity matrix, this is the same distance as Euclidean distance. But when we have sigma as non-zero, or in other words, we have access to what sigma is, we should be able to get something called Mahalanobis distance. So how do we derive sigma? Very simple. It's basically covariance matrix of your data generation process. Given 10,000 data points x, I will be able to construct C is equal to x transpose by n minus 1. C, in fact, is the covariance matrix or sigma, and then we need to take an inverse of it. So just trying to understand covariance matrix is also a very important factor. So generally, we know what variance is. Given this kind of a data distribution, I'll be able to tell you that variance is how your data point varies across different values of your x, right? Given a mean in this case, which is 0, I can say that 95% of my result is going to exist within something like 0.4. 95% of my possible samples can exist within 0.4 to minus 0.4. That would be the variance, 95% variance in this case. This is for a single dimension. I'm just looking at x. So this is for a single variable. I'll be able to tell you what x is. But let's say that you have another dimension, which is x2, which is another feature. Covariance matrix is how each of those data points vary against each other. So one way of thinking about it is, let me try to draw this. I'm not sure if it's, so if your data point is like this versus something like it's like this, right? Is it easy to see? But basically, you need to think of it in a 2-dimensional sense. If I do a top-down view of what I drew, so it is going to look something like this. So this is 95%. It is going to look something like this. Now, if I were to say that the variance is going to be like this, in other words, this is going to look something like for the second dimension, my 95% is going to be a smoother curve, which means that there's going to be a longer or a much larger variance across this. So the difference now is how my x1 is going to vary against x2. It can vary in 2 ways. It can vary based on the blue curve, or it can vary based on the red curve. And that is something that is going to be denoted by my covariance matrix. How sigma of xy and sigma of yx and xy, how these 2 things are going to interact with each other is going to be given by my covariance matrix. If all we are concerned with is sigma xx and sigma yy, in other words, if we try to look at this separately as this and this, then we are thinking of this from a naive-based setting where each of the features are not affecting the other, but that is not true, right? Both of these features are, x1 and x2 are affecting each other. So it's not an independent of feature setting. It's x1 affects x2, x2 affects x1. If you look at the slides, I think it's written as y and x. In other words, I'm saying that x affects y and y affects x. So these two random variables are going to be affected by each other. And the way they affect each other in a Gaussian setting is, in a second order setting at least, is given by something called covariance matrix sigma. Sigma inverse, it's called something called a precision matrix, and that is what we are going to use in Mahalanobis distance. We are going to use that as our metric. There's an example here regarding how we use this kind of a Mahalanobis distance. This is exactly telling you what I showed before, which is given x1 as 0.5, 0.5, x2 as 0.1, x3 as 1.5, 1.5, and we are just giving you this covariance matrix. If this is accurate, then you can actually take the inverse and find that sigma inverse is something like this, and you can find the covariance, you can find the Mahalanobis distance between x1, x2, x1, x3, and see that the distance between x1, x2 is higher, which is 5, compared to something like x1, x3, which is 4. But again, if you actually look at the results here, that doesn't seem to be the case. The measurement between x2 and x1 seems to be much lower than x1 and x3, which in fact is not true from a Mahalanobis distance setting. So what you're doing in Mahalanobis distance, which is very important, is considering the data distribution into consideration, which you have not previously. All distance measures are seen as just measurement between 2 points, but then there's this entire 10,000 elephant that is behind the two data generation, the two data points that you're looking at, which is very important to take into consideration as well. Any questions regarding Mahalanobis distance? Yes. Why do you think this is in fact based on the so inverse of covariance matrix is something called precision matrix, and the way precision matrix is defined is that it tells you how each of the features varies across a single axis. So the derivation of it is based on mean square error. Same thing that we have done before, but this time there's an involvement of the features themselves. So even though it's based on the precision matrix, it's just that it has a more common name in terms of covariance, and that's why we represent it in terms of covariance matrix, which is sigma inverse. But the actual thing that I talked about, which is the variance across, or is called the precision matrix. That's it. All right. If no other questions, then we can move on to the next part, which is talking about clustering methods. And the most important clustering method is k-means clustering. So a lot of today is going to be discussing about just this aspect, which is k-means clustering. We'll start off with the problem statement. This is the exact problem statement that we had from before, which is the definition of clustering itself. Given a lot of data points, x1 to capital Xn, with each element x1, x2, xn, is a set of features from 1 to capital P. Our goal is to cluster them into a specific number of clusters K. In this case, those clusters will be represented based on something called, in this case, centroids in k-means clustering, which is given by C1 to Ck. And these three factors are the same thing that we had last lecture as well, which is the definition of what clustering is going to be. The number of cluster K, we're going to define it previously. Each sample is assigned to a cluster, which essentially is what we saw last time. A union of every single point is going to give you the entire data set. In other words, every point is related to a single cluster. And the proximity distance that we'll be using, the proximity measure that we'll be using for k-means is the Euclidean distance. Samples in CJ has smaller Euclidean distance in sample, not in CJ. So the way we'll say that a particular data point belongs to a cluster is by looking at the Euclidean distance of that point from that cluster and from all other clusters. If that cluster has a smaller distance, then the sample belongs to that particular cluster rather than anything else. So each cluster CJ has a cluster center. This is called centroids, which basically C1, C2, Ck are our different centroids here, represented by mean of all samples. So I think this will become more clearer when I show you the images, but essentially the way your centroid is going to be defined is just as a mean of all the features that are present in the cluster. So it's probably more easier to look at the algorithm itself rather than that just one sentence, because that one sentence is what the algorithm is going to be. So let's start by looking at the right-hand side here, which is you have all these data points in step number 1. The goal for us is to make clusters out of them. So this is how we start with in step 1 regarding data, and what we want to end with are these spaces. We call this Voronoi spaces. Essentially, we want to divide this entire space into different sets, and each of those sets are going to be the separate clusters. We represent it using these colors in this case, and k-means algorithm allows us to go from this unclustered data on the top left down to the clustered data that you have on the bottom right over here. So step 1, now we'll move to the actual algorithm itself. Step 1, we'll start by choosing some 3 data points. In this case, the red, the green, and the blue. So these are the 3 data points that we'll start. Let's just assume that we are just doing from a very random state. We are saying that these are our 3 centroids to begin with. And then this essentially we are randomly choosing k samples from data set. So this part is something we'll discuss in a bit, but let's just start off by looking at k samples as our data set, which is going to be that in our entire data set that we'll have capital M number of samples, we already know that I want to choose k samples as our centroids. Now, how we do that is something we'll discuss later, but let's start by saying that I already know that I have the value k, and I'm going to choose these 3 options as my, randomly choosing some data points as my centroids. The next step is something that we'll be calling as the assignment step. So assign each data point xi to the cluster Cj with the nearest centroid Mj measured by the Euclidean distance. That means that given this kind of a data set, I've already started with these 3 centroids. Now my first thing I am going to do is calculate the distance between these 2 points. Record it. Calculate distance between these 2 points. Record it. Calculate distance here. Record. Distance here. Record. Distance here. Record. Here. Record. And every single data point that exists in my data set, I'm going to calculate the distance from a given centroid and record that. And I'm going to do that next for the green thing. I'm going to create a table. I'm going to choose the nearest samples, nearest centroids for those particular samples and assign them. And that is going to give me this kind of a centroid. Is this step clear? So I'm creating this kind of a, there's 3 here, so there's going to be 3 columns. But 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's going to be 12 rows. So it's going to be a 12 cross 3 column, where all I'm doing in this case is recording distances from each of the data points to a particular centroid. And once that is done, I'm going to choose the one with the lowest in that row. So let's say I'm looking at this sample. Let me call this as x10. So in x10, my distance to row number, this will be red, this will be green, and this will be blue. So for x10, my distance from red is going to be something like measurement of 7. Distance from green is going to be something like 4. And distance from blue is going to be something like 3. So these are distances that I'm going to calculate, which is a Euclidean distance. And once I get these distances, I'm going to say that 3 is the least number. Right? So that is the, across this row, the minimum distance that I have for a data point is for the blue cluster. Hence, I'm going to say that this is belonging to the blue cluster. Actually, probably I should have done the opposite. So let me do this, 3 and 4 here. So 3 and 4. So x10 data point, which is this, has the minimum distance 3 for the green cluster. So now I'm going to state that x10 belongs to the green cluster based on this distance. It's a very simple way of just assigning based on how far it is from each of these clusters. It's a brute force way of assigning how far it is from every single cluster. So that is step number 2, which is assignment step. The next step is the update step, which now that we have assigned everything, maybe our initial choice of our centroid was incorrect. Right? Because how did we start by choosing centroid? We just said that these k samples are my centroids, which may not be correct. This is a randomly generated process of finding the centroid. So it may not be correct. So the goal in step number 3 is to update the centroid itself. Given these kind of partitions right now, I am going to take the mean of all these centroids. So the mean of these two things, the mean of all these things, and the mean of all these things. So in this green case, there's 1, 2, 3, 4, 5, 6. There's 6 data samples, right? So I'm just going to take a mean of all these data samples, which is going to now move my centroid that was here at iteration 1, let's say, down to this at iteration 2. So now my centroid itself has moved. I'm just fine-tuning where my centroid needs to be in the next something called update step. And I do the same thing with red as well. So this has now iteration 1 to iteration 2 has now moved. Blue as well. Iteration 1 to iteration 2 has now moved to a different place. I'm not sure I mentioned this, but centroids don't need to be data samples themselves. They could be some points within these larger spaces. It's just a mathematical quantity for us. It's just a mean of all the features that exist within that, that space in this case. So that is step number 3, where mean of the centers are taken as the centroids. Step number 4 is essentially we keep iterating through this process. Right? Now that we have a new centroid, I can now create another matrix, another 12 cross 3 matrix, distance across different data samples that exist. So based on that, I can have a different partition, which we have here. Now again, I can move back. I can say that my centroid, I can reassign values for the centroid and keep on going forward. And this is a process that keeps on occurring until some convergence limit is reached. So we'll talk about what that convergence limit is, but any question in terms of the algorithm itself. K-means clustering is the most important clustering algorithm there is, and the first thing that you should always try whenever you have a clustering problem. So in terms of convergence analysis, so we'll have 3 criteria that we will use in order to stop this iteration process of the assignment and the update step. The first one is when the cluster membership becomes static. In other words, if I go back to this image, maybe the clustering is not changing. So look at the difference between step 2 and step 4 here. The cluster spaces themselves have changed. In other words, some of the data samples that were in red have now become green, some of those that have been in green are now red, and so on. But if this becomes static across different iterations, that means that nothing is moving forward. Your k-means algorithm has now found the best possible clusters, hence you can stop your algorithm. Another way of deciding how to stop your k-means algorithm is to see that there's no change within the centroid itself. In other words, the difference between step 2 and step 3. Maybe your centroid, in this case, you see that there is a large change, right, between your 2 reds. There's a small appreciable change within green and a small change within blue. Maybe you do this process across 10 different times, and 11th time you notice that there is no change in your centroids. That is when you can stop doing the clustering. You can stop you don't need to do a 12th iteration. Then the last one is change in the cost, which is sum of squared Euclidean distance, or SSD, which basically means that there's no change in this table. You've constructed this table, and you have said that the total cost for x1 is something if I take the cost across the columns, that means it's the cost for a particular cluster. So for red, the cost would be 7 plus, I don't know, this could be something like 4, 3, 1. So the cost for red is 1 plus 7 plus 4 plus 3, which is something like 15 essentially. So if that cost does not change across different iterations, that is another criteria for you to say that, okay, I'm done with my k-means clustering. I don't need to do anything going forward. So if any of these 3 clustering, if these 3 criteria are met, you can stop doing further iterations within the k-means clustering algorithm. So that is from a convergence point of view, what is happening within k-means. Again, this will become a little bit more clearer once we follow this example. Let's start off by this full data point. Yes?
What do you mean when you say that this is the
Most
most important clustering algorithm? Is it just most commonly used?
commonly used, and the first thing that you need to start with, if you have a data set that is unpartitioned to begin with, and you're looking to try to understand something about the data, again, we are looking at unsupervised learning algorithms. So we don't have labels. We don't know what this data looks like. And usually, this is just two-dimensional data. But if the data set is let's say even four-dimensional, you won't be able to visualize it directly without doing dimensionality reduction. So the first thing that you need to start off with is by looking at k-means clustering and saying that, okay, there's only 3 important data points or centroids within this entire data set, and I need to start analyzing by these data points. Anybody, anywhere. K-means clustering is as you said as well, it is the most commonly used clustering algorithm, so that is what you need to start with. Of course, it also depends on data. For instance, if you're working on something like time series data, biometrics or health data, K-means is not a good thing there because we are using Euclidean distance, and if you have a time series data, take a simple sinusoid for something like this. If you're trying to compare this against a slightly shifted sinusoid, in the frequency space, we know that it's a very small shift. It's like a pi by 8, pi by 16 or something like that. But if you start taking the distances between data points, it adds up. So this is like at every point, there's a difference of about 0.1. So 0.1 multiplied by the entire time series, it adds up. So k-means in this case is not going to be a good methodology. There are other ways. But based on if you know nothing about the data itself, then k-means is something that you would have to start with. So given this data on the left-hand side, again, the first step is to randomly start choosing m's, which I do, m1, m2, m3. I'm just predefining k to be 3 in this particular case. So the next step is I'll start assigning. I'm going to create that table across the entire data set and assign different data points within the centroids, and I'm going to get these Voronoi spaces where the spaces are, this is space 1, this is space 2, this is space 3. And there are data points that exist within this particular space. The next thing I do is update my centroid. Now, if you look at where my initial chosen centroid is, this M1, and look at this space over here. M1 is not a good choice, right? Most of the data points is concentrated at this spot, while M1 is somewhere over here, which may not be a good choice. That's why I would have to update the centroid right now, which in this case from here, it is now going to move here, which seems a little bit more practical. This is where you would want your M1 to be across with the other data points in this cluster. Right? So this is essentially what we are doing with the update step. We have updated our centroids based on the data points that we think are within this cluster. But now this creates a problem, because if I look at M1 and I look at this particular point here, this point that is in circle is nearer to M1 than it is to M2. And this is when we have to go back. In the second iteration, we are doing our assignment step in the second iteration, where this data point is now comes to, I don't know if it's very visible here, but the top part is orange, here it's red. So the red point, which was there before, has now become orange in this case. It has moved to a different space, a different cluster. Now, based on that, I can again redo this kind of a update step, which is essentially I can now move my M1 a little bit further. It needs to go towards the right in order to accommodate the new data point that has now come within its purview, within its cluster. So M1 has now moved to a different spot. And now this has again created another issue, right? Which is that since M1 has now moved very far away, this data point here, which is currently in a circle, is now very far away from M1, which means that you need to reassign that back to a different spot. So the assignment part now is going to be different. So this spot in circle here, this data point, now belongs to M2 cluster rather than M1 cluster. And this is now your space has changed again. And this keeps on repeating until you get to a certain stage where you'll be able to say that all my data points are within the required clusters. I believe that this is the end for this example. Yeah, for this, there's no, so given this kind of data space, there's no reassignment that needs to happen. In this case, we have to move our M2 and M1 bit. Our centroid has to move a little bit. But the next step, when we go to the next iteration, there's not any movement that happens. That means that the algorithm, if we are using the first convergence criteria, which in this case is going to be, let me go back to this, cluster membership. So cluster membership has now become static. In other words, there's no change that is going to happen in our fourth iteration, which means that I have finally found convergence within my k-means clustering algorithm. So this is more of an example of k-means clustering algorithm itself. So now we move to the strengths and weaknesses of k-means clustering. So let's start off by looking at what initialization does for us. So first off, our choice of k is very important. This is something similar to k nearest neighbors that we saw during classification. We have to choose k, and it's not always easy to choose what k is. We have to, and sometimes, based on the fact that if you have k equals 3 or k equals 8, your results are going to look very different. And even based on where you have chosen what these k values are going to be, you're going to get very different results. So for instance, if you're just using k equals 2 in this randomly generated data, just by visually inspecting it, I would say that a more correct clustering is this and this in the dotted lines. But if you have randomly chosen your initial k points to be these two things on the left, you'll probably end up with something like this in iteration 2, and your algorithm is going to converge, because if you're just looking at membership, there's not much membership that is changing. So your choice of k might be very relevant, and where you have randomly chosen it in the beginning, again, it's random, so you know it's not in your hands if you use the vanilla standard algorithm, but it might be incorrect. So we have to have a good analysis of the methods to initialize these k centroids, and also choosing the right number of k. We'll discuss what this means in the next few slides. So choice of k, similar to k nearest neighbors, the usual thing that we do is treat it as a hyperparameter. And if we treat it as a hyperparameter, that means we need to do cross-validation and find the best k, essentially. Or we can run across different values of k and see what the best results are. And best results would mean this kind of a table. So sigma j equals 1 to k, xi belongs to cj, essentially means that you're creating those tables and calculating the cost. So for a particular value of k, you just add up all the values in that table and say that the value is like 25. For a different value of k, the value might be something like 35. In which case, obviously, the 25 is better, right? Because the distances are going to be lower. So you can use that as a methodology to initialize which k value you want. The last one can be domain knowledge. Sometimes the values of k are given to you based on your problem definition itself. So in this case, I think we have written, for instance, when we want to cluster cars sold last year, k will be the number of car manufacturers in the market. Right? So if you have, 10 manufacturers in the market, you want to cluster based on the number of manufacturers of cars. Maybe one of them has no cars sold, so then you would have to say, okay, it's based on 9 car manufacturers. But sometimes k is given to you, in which case you have to use the k values that you begin with. So in terms of choice of initial constraints, so there's a lot of methods, a lot of papers that tries to come up with good strategies. So this particular slide, we're just listing a few things, but again, this is just more for your information rather than anything that will be either asked in the homework or in exams. This is more for you if you're interested in trying to understand how a simple standard vanilla algorithm like k-means can be constructed into research papers. Essentially, you just start looking at where the variability is and try to find the best methods in order to address those variabilities. So that leads you to all these methods and papers. So what we saw till now was the RP, which is the randomly selected points. So we look at one other thing in this class, which is the k-means plus plus. But all the others, again, are more for your information if you're interested in going through them. So k-means plus plus algorithm, instead of taking k centroids to begin with, it starts off by taking a single centroid. This single centroid is taken randomly, and once you do that, you construct a table. Even before you consider any centroids, you construct just a one-column table of centroid M and all, 10 data points that you have, and then you select the ones with the highest probability of them being a centroid. And the way you calculate the highest probability is by this formula here that we give in step number 3. In other words, you start off with a single centroid. So do I have a... So I don't think I have a... so given this kind of a methodology, right? So let's look at this thing. This, we said that this initial choice was an issue. So the way we would address this in k-means++ is to start off with this point, with this star point over here. Then we'll construct a table across all data points. If there's about 10 data points here, then it would be one column with 10 data points with the star as my centroid. I'm trying to draw a star. I don't think that worked very well. But based on this one star, I'm going to create all these distances, and I'm going to select two other, or I'm going to, in this case, I need to select one, right? I would select the one with the highest probability, which is defined by a distance. So in this case, the one that is furthest away from the star is this point here. So what k-means++ is going to do for you is it will not allow you to choose this star as your second centroid. It will say that it has to be something that is very far away, which in this case is going to be this. So then that means that you won't have this in your iteration 2. You will probably end up with something like this and this, which is ideally what you want in your clustering. So k-means++ is just a way for you to design a strategy where of choosing your centroids better based on choosing your centroid in the first part. Again, the first one is random. The first centroid you're choosing is random. But once you establish what M1 is, then you start deciding what the closest value is against all particular data points, and then create this kind of likelihood probability function and use it. Any questions in k-means++? Yes?
What's the probability proportional?
Which one?
Step 4.
Choose next centroid from dataset at random with probability proportional to p. So in this case, you create that column, that kind of a table. So each of those table is going to be filled with this p of xi. So for a distance p of xi, for a data point x1 to x10, you're going to construct that particular table. So in the next, choose next centroid from dataset at random with probability proportional to p. So if you want a probability density function of, let's say, a Gaussian probability density of something like this, where you're saying that the distance has to be p of xi. So you're now choosing samples that is closest to this, right? Because this is not going to give you so you're not looking at them as samples themselves. So this is essentially a point that you don't need a sample in. But when you start off your random sampling, you want to choose the one that is closest to that. So that closest is given by this probability proportional to that p. So whenever I say that this particular point here is your centroid, I don't mean that it's a sample. I mean that it's something that may or may not exist. I don't know if I have a similar case here. So you see M1 here, right? M1 is not a data point to begin with. It's just a point in this space. It's not a sample itself. So that means that as soon as I find the proportionality, the column, I need to find the one that is closest to that proportion, to that probability, and choose that as my centroid to start with. So the good thing about k-means clustering is, of course, that it's very simple and easy to implement, and the time complexity as well. Whenever you see something like this, O refers to the order, and T multiplied with K multiplied with capital N. In other words, you'll usually see this. If you read any papers, if you read any notes, you'll probably have already seen something like order of N, which is essentially what T of K, Tk, order of Tkn is. Because T and K are very small compared to capital N. We usually have data points in the thousands, tens of thousands, but the number of centroids that we are going to have, which is K, is going to be very less, let's say 5 or 10. Right? So it's still linear with respect to capital N. Same thing with T as well, which is the number of iterations you will have to do in every step. Ideally, if you choose a good starting point, then you won't need as many iterations in order to get to the best k-means clustering algorithm. So it is going to be order of N. In other words, it's going to be linear with respect to the number of data points that you begin with. It's also the most popular clustering algorithm. And k-means algorithm does not guarantee convergence by a global optimum if SSD is used. SSD is the sum of squared distances, which is already, we saw that, right? So we saw in this case that this may not actually be the global optimum if you're using Euclidean distance. But this is more of a, we'll talk about variation of k-means, so this will help us. Euclidean distance may not be the best strategy. Maybe there are other kind of distances within the same framework that we can use. So the weaknesses, we already discussed this, which is that the user needs to specify what k is. The algorithm is only defined if mean of the cluster is defined, and for categorical data, this may not be the best thing. So if your outputs are in terms of 1, 2, 5, and your mean is in terms of 4.752, you don't really know what that means. So in that case, you would probably use something like k-mode clustering, where mode is the most frequently occurring data sample or most frequently occurring feature in a particular dimension. The most important problem within k-means clustering is the last one, which is the algorithm is very sensitive to outliers. Your outlier in this case, your ideal clustering, if needs to be something like this portion, it should be here, right? But then if you have access to outliers, what happens is that this outlier, your mean centroid is going to be somewhere here just because of this presence of this outlier. So you'll not get the correct clusters if you have these kind of wrong data points, or what we would call outliers in this case. There are a couple of ways that you do it. If you're hellbent on just using k-means clustering, then the best way is to kind of ignore it. You can either remove it, or you can do random sampling and say that hopefully in most of these samples, my outlier is not going to be part of my data set. But there are better ways, and we'll discuss a few of them, which is the k-median clustering is there for the outliers. So the first variation, so we'll discuss about 3 different variations of k-means clustering itself. In fact, I think there's 4 different variations of k-means clustering. The first one, and we'll go quite quickly through this. It's not, it's more of an extension of k-means clustering rather than their own algorithms. The first one we can do is do something like mini-batch k-means clustering. It's very similar to stochastic gradient descent, mini-batch gradient descent, and batch gradient descent that we were looking at before, right? So instead of taking the entire data set and constructing this n cross k table every single time, maybe we take a small batch. Instead of taking 10 data points, for instance, we'll just take 5 data points at every single iteration and every single step in order to create our table. And based on those tables, we will assign and update our algorithm. That is essentially what mini-batch k-means clustering does. So what you usually notice is that the convergence, the mini-batch k-means clustering, is much, much faster than a k-means clustering algorithm. And good thing is that it won't be, the results themselves won't be as different. So in this particular case, this is a real life example where this is how k-means clustering, if you use k-means clustering, this is what it's going to look like on the left hand side. The middle portion is for mini-batch k-means clustering, where you'll be using just a smaller subset at every single iteration in order to create your update and assignment steps. And the only difference are these purple dots here. Between the k-means and the mini-batch k-means. So if you don't have outliers, mini-batch k-means clustering helps you make it faster with only a small number of differences in terms of accuracy. It's not given 100,000 data points, maybe you're just losing out on 10, 15 data points in terms of accuracy, but you're gaining magnitudes in terms of speed. So that's why mini-batch k-means clustering can be a good alternative to the entire k-means clustering, which in this case we'll call as batch k-means clustering. Again, the only difference, of course, is going to be that we'll randomly draw B samples from the data set to form mini-batch, and every single iteration update step is based on these mini-batches, these B samples, rather than the entire capital N samples. That's the only difference between mini-batch k-means clustering and k-means clustering. So that is one variation. The next one is k-median clustering. So I think we all know 3 major statistics that exist, which is the mean, median, and mode. K-means clustering, median is just basically the second one, which is we are looking at the median data point, or the median point within the data space. So in this case, your mean is going to be something like this, versus if I look at the median across different features, it is going to be something like this. If I look at it per feature, that is what we would call marginal median, which is you take the features themselves, order it, and take the middle feature. That essentially is what we would call the the marginal median, versus the median is we take everything together, all the features together, and find what the median data point is going to be. So that would be about the k-median clustering. The only difference, of course, is that the assignment is now made on this the median algorithm rather than on the mean algorithm in the assignment step, which is where we take the table. So initialization is still the same thing. We take k samples from the in data points as initial samples, and the assignment step is going to be based on this median rule. In a higher dimensional space, this goes down to a Manhattan distance, because as you know, if we are looking at the median thing, it's basically we are looking at distances across a single dimension. We are ordering that, and if we take the middle portion of it, which is going to be the Manhattan distance in this case, the update can remain the same, which is you just need to move your centroid to a different location. It could be the same as your k-means clustering. The difference, of course, is going to be only in one step, which is the assignment step in this case. So the next one after that is going to be about the meteoroids clustering. So until this point, we have treated this centroid as some point in the space. It's not a data sample. It could be, in this case, I think it's best represented here. So whenever we did M1, M2, we did not say that it has to be samples. M2 could be here, right? If it was sample, then maybe this should have been the centroid. If I zoom in a little bit, then this portion here, which is closest to this point, should have been the centroid. But we did not say that. Sample could be a sample by itself. It need not have been a sample in k-means and k-median clustering. The difference in k-meteoroid sampling is that my centroid that I'm choosing should always be a data sample. It should be part of your data set. Instead of thinking of it as an arbitrary centroid, it is now a data sample within my data set. If we are going with that assumption, then what we are doing is k-meteoroid clustering. So in this case, k-meteoroid clustering. So meteoroid is defined as the data point of a cluster whose average dissimilarity to all the data points in the cluster is minimal. Essentially, my centroid right now is a data point. That is the most important, that is a major difference here in k-meteoroid clustering. All the other parts will still remain the same. You still are going to use some kind of a distance in order to create that table. Now, k-means clustering is for Euclidean distance. K-median is for L1 distance. Meteoroid is not defined. You can choose any distance measure in order to create your table. In this case, that could be either an L1 or an L2 norm. And this k-meteoroids can be used with arbitrary distance functions, which is a generalization of the k-means and k-median function. That's why this is more of just a D given xi comma m, which is your centroids in this case. One major difference in the way the algorithm is constructed as itself is that we always need to swap m and x. So until this point, we really did not care what the update step would give us as our solution. It could be an arbitrary sample, or it could be an arbitrary point within my cluster space, right? But now we want a sample as our centroid. In other words, once we have an m and we are updating it, we can't simply just take mean and use that as our centroid. We have to update it. We have to swap it for an x. All other parts are still the same. It's just that the swapping is going to be different. And maybe this is best illustrated through an example. So the next few slides have that kind of example. So given all this kind of our data distribution, our goal is now to create a clustering algorithm based on k-meteoroid methodology. So let's start by using k-meteoroids and L1 norm distance, Manhattan distance. Cluster the following data points into two clusters, which is given by k is equal to 2. So let's start off by initializing something. Let's say that this point here is one of our clusters, and this other point here is any cluster. So in other words, I'm just using this point and this point as our two clusters, randomly chosen. Based on that, I create the table, which we have been talking about. And since we are doing an L1 distance, it's more easier. L1 distance, basically, let's say x1 to x4, right? So there is 1 distance, and there is 2 distance. So 2 plus 1 is 3 across different feature dimensions. And I'm using that as my 3 in this case, as my distance. I can use this and create this table across different across different medioids and construct this table. The total cost, again, is something we had talked about before, which is if I want to use x4 as the centroid, then the cost of that is going to be 13. If I want to use m2 here as a centroid, the cost of that is going to be 11. So the total cost of clustering is just going to be 13 plus 11, which is going to be 24. Now I can start checking for individual things. So let's say that I'm not happy with m4, x4 as my centroid. I start creating distances against different methodologies. So if I say that x2, 6, which in this case, so this is when x1 is centroid. So I basically have created a distance map based on x1 being the centroid, which means that the distance between x1, x2, which may be, so this is distance between, so 0 equals distance between x1, x1. So the 3 is equal to distance between x1, x4. So again, 3 is the distance between x1, x2. So 0 plus 3 is in fact the distances from each data point to the other data points that can exist, which is essentially what we are doing here, and we are calculating the total cost. By looking at this, we saw previously that the medioid distance was 13. Now that still remains the lowest distance. x4 is still my best bet to be the centroid, right? All the other costs are pretty high. So that means that nothing changes here. But if I do it for the second cluster, so you'll clearly notice that x9 here is not a good cluster, right? Not a good centroid. This seems like the best bet for our centroid, and that is kind of seen here. So if I do the same table where I do the distances across the things and calculate the cost, I get a 7 cost when I'm using x7 as my centroid, and this is against 11 that I had before, which means that my new centroid in my update step has now should be swapped. So x7 should now be my centroid rather than x9 that I began with. Previously in k-means, there was no swapping. All you had to do was calculate a mean and you would get your new centroid. In this case, you have to swap and say that 7, 3 is my new centroid based on the cost that you have created. That is the only difference and the major difference between k-means and k-medioid clustering. With that, you get a correct solution in terms of what the clustering results are going to be. You can, of course, do multiple iterations, and until you reach convergence, you have to keep on doing the swapping to get the best possible solution. So that is about the k-medioid clustering. The last one is about fuzzy clustering. We'll cover that on Wednesday when we do Gaussian mixture models.